Welcome year 11s. This is a tutorial videos about chapter 2E, parallel and perpendicular lines. So what we're going to do today is to recap the concept of gradients in parallel lines as well as in perpendicular lines. We're going to also dive in to try to prove the concept. Okay. Now, let's firstly recap. This is the concept you have learned since year 9 or 10. Okay, so it should be pretty straightforward as for the concept here. So if you have two straight lines like that, they are parallel. Okay, so we're going to list their equation, which is in the general form. These are the general forms, right? So y equals m1x plus c1, and this one we have y equals to m2x plus c2. All right, now we know that if the two lines are parallel, their gradients will be equal, right? And since we still be able to see two distinctive lines, that means the y-intercept should not be equal. Okay. All right, now let's think about how we're going to prove how to prove that the gradients are equal in parallel lines. Okay, now in order to prove this, we need to use the concept of angles or angle relations in parallel lines. Okay, so I'll just put one arrow. All right, now I'm just quickly recap about the concept of the angles in parallel lines. Okay, so first of all, you see these two lines are parallel, and then I just draw the third line, and then this line is called the transversal line. Okay, the transversal line. Now, in this relationship, we find there are a few angles there. So first of all, we start with this pair of angles. Okay, so we call this pair of angles as corresponding angles. Yeah, corresponding angles. Okay, so and then we have using a different color, and then we have this pair of angles. So we call them alternate angles or alternating angles. Yeah. And finally, we've got these pairs. Okay, so these two are called co-interior angles. Okay, now we know that in corresponding angles in parallel lines are equal, right? Are equal, so equal size. Okay. Alternate angles in parallel lines are also equal. Yeah. As for co-interior, they are not equal. But what are they? They are in a relationship. They are supplementary, right? They are in supplementary relationship. They are supplementary. Okay. So since we know that, we're going to try to prove this. Okay. To try to prove the gradients in parallel lines are equal. Sketch an axis. You got the x and y. Okay, so I'm going to just draw two straight lines there that they are parallel. Make sure they're parallel. Okay, now, and then I'm going to pick two angles. We know because these two lines are parallel, this is our condition. So we know these two, which are the corresponding angles, they should also be equal, right? It should be equal. So let's give this angle, let's say theta. So these two angles should all equal to theta. Okay, now just record the gradient for this red line. It is m1, and the gradient for this line is m2. Okay, so we note that the the gradient can not only represented by rise over run, or the difference of y's and x, y2 minus y1 over x2 minus x1. We can also using this angle. Okay, so more specifically, this angle is the angle that between the straight line itself and the positive direction of the x-axis. So here you can see the gradient, it is equal to the tangent. Okay, the tangent of this angle. Okay, so tangent of theta. Therefore, m1 it is equal to m2. Yeah, and we can also label the y-intercept for each of the lines. So here you can see this is going to be c1, right? And here this is going to be c2, right? And let's label the equation first. So now you can say that the gradient should be equal, and the y-intercept are not equal. Okay, so this is how we prove the gradient relationship in parallel lines. With perpendicular lines, again, let's quickly recap about the concept itself. So if you get two lines that are perpendicular, like so, we have the y equals to m1x plus c1. This we have y equals to m2x plus c2. All right, we know that if the two lines are perpendicular, m1, m1 times m2, it is should equals to -1, or we say m1, it is -1 over m2. So this relationship is called a negative reciprocal relationship. Okay, now let's see how we're going to prove this. We need to recap the concept of a congruent, okay, congruent triangle. Let's take a look. So I'm going to draw axis here. All right, so I'm drawing the first one. The first line that is okay, so that is passing through this origin. Okay, so this is the first line, and then let's do a second one that is perpendicular, both passing through the origin. Okay, all right, now for this one, let's say this got y equals to m1x plus c1, and here we got y equals to m2x plus c2. Okay, so some of you have noticed that since both lines passing through the origin, that means they have 0 c's. Okay, so let's make it life easier. Just get rid of the c for now. Okay, so let's make a condition that these two lines are perpendicular. I'm going to making this distance. Okay, so this distance that is equal to the distance over here. Okay, so these two distances are equal. So this is our condition. We can form in two triangles. Right? We can form in two triangles. And I'm going to label the vertices. So that is all here. And we got A, B. Here let's do D and C. Okay, so now we need to prove the two triangles are congruent. Okay, because in order to prove the gradient relationships, we need to firstly find out relationships about few corresponding sides. Now, we firstly know two angles. Okay, so we know that the angle BAO, it is equal to angle OCD, because both they are right angle 90 degrees. Okay. Secondly, we got a pair of sides. The pair of sides are OA. It is equal to DC. Okay, so this is given. Okay, so we got a pair of angles, the same pair of corresponding sides, the same. We still need one more. Okay, either one more pair of sides or one more pair of angles. Now, so some of you may think because we got a right angle triangle, we got a pair of the shorter side, we got a pair of the right angle, can we using the hypotenuse? Now, according to the current information, we can't prove it, right? We can't prove it unless we know the coordinates of D and B so that we can find the distance between. Now, but unfortunately, we don't have the coordinates, so we can't just prove the hypotenuse are equal. Instead, we can use the angles in the middle that is being 90 degrees. So what we can do, we can say since, okay, so because angle BOA, right, plus angle DOB, which is 90 degrees, that plus angle DOC altogether, they will equals to 180 degrees, okay? And also the angle DOB, it is equal to 90 degrees. Therefore, angle BOA, which is this one here, okay, plus angle DOC, which is this guy here, these two should equal, add up into 90 degrees. So they are complementary, okay? We can also find out that the angle ODC, okay, this is ODC over there, ODC plus angle DOC are also 90 degrees, okay? So now you can see that there are two different angles adding the same angle equals 90 degrees, which tells us that angle BOA is equal to angle ODC, yeah? So these two are equal. So now we got the pair of angles, pair of sides, and a pair of another angle. So we can now say the triangle OAB, it is congruent to triangle DCO, okay? So we're using AAS, yeah? So this is a testing method, AAS. Okay, now since the two triangles are congruent, therefore, right, CO is equal to AB. Okay, this is what we're trying to find. All right, now let's try to represent the gradient for each of the line using the tangent, okay? So using the tangent of the angle. Now, so here, for M1, so this is the angle here, okay? That is formed by the straight line itself and the positive direction of the x-axis, right? So for this particular angle, it's actually angle BOA, right? BOA. So we can say gradient. Okay, so zoom out a bit so you can see the diagram. So M1, it should be equals to tangent, okay, of angle BOA. Yeah, tangent of angle BOA. So what is the tangent of BOA? That is the opposite side of the angle BOA, which is AB, right? Over the adjacent side, which is OA. Okay. All right, now let's do the second one. So M2, what's M2 equals? M2 equals to the tangent of the angle. Okay. Now here there's something that you also need to remember, which is, firstly, the angle that we refer as is always the angle that is formed by the straight line and the positive direction of the x-axis, which means this angle is the one that we refer as. Okay. So this angle is going to be, it's going to be angle DOA. Okay, now how can I represent this angle again? Well, this angle is going to be negative since it's in second quadrant. Remember, in unit circle, the tangent in second quadrant is going to be negative, right? So it's a reference angle is going to be DOC, okay, DOC. So so DOC have its opposite, which is DC, and the adjacent CO. Okay. All right. Now, so we got the ratios of the sides. Now, since we have proved the two triangles are congruent, we can replace in DC and CO in terms of OA and AB, right? So I'll be putting this to the side a bit so I can continue right here. We know that DC, it is equal to OA, and CO is equal to AB, right? And don't forget, very important, we have a negative. Okay. Final step, let's try to multiply M1 and M2. Okay, when we're multiplying them, what we get here, it is AB over OA times negative OA over AB. So we can cancel the ABs, cancel the OAs, and we only have a negative 1 left. Okay, so this is how we prove gradients in perpendicular lines. Okay, let's quickly take a look about this example here. Find the equation of the straight line that passing through 4, 5 and is parallel to y equals to negative 2x plus 5 and perpendicular to 2x minus y equals to 6. Okay, so let's try to solve part A first. So for part A, so what we do with part A? So part A, you need to firstly relate to this existing straight line equation, right? So before we do that, we have to write our general equation of the straight line, y equals to mx plus c, okay, like so. So we're trying to find m and we're trying to find c, so that we can determine the equation. So because it says it's parallel to this straight line, so we know that the m, it is equal to negative 2, right? M is equal to negative 2. And then we can rewrite the equation such as y equals to negative 2x plus c, okay? Now, this c clearly should be different from the existing equation, which is 5. So how we could find c? Well, we're going to use this. We're going to use this point, okay? So then we're going to substitute 4, 5. So let's put in, so we got 5. It is equal to negative 2 times 4 plus c, yeah? Negative 2 times 4 plus c. So we got 5. It is equal to negative 8 plus c. Therefore, c should equals to 13, right? C should equals to 13. Therefore, y, it is equal to negative 2x plus 13. Okay, so this is the equation that is parallel to y equals to negative 2x plus 5, as well as passing through 4, 5. Okay. Now let's take a look about the part B here. Okay, for part B, before we do anything, firstly we have to convert. Okay, we have to convert this equation there, because it's not in the general form where we can see the gradient and the y-intercept straight away. Okay, fortunately this is easy enough for us to transpose. All we need to do is to just moving few terms, moving the y terms and also the 6 term here, right? So copy that, write the equivalent general equation for this one. We got y, it is equal to 2x minus 6. Yeah, 2x minus 6. Okay. Now, let's write the general equation for the straight lines we're trying to find. And since we know they are perpendicular, m is going to be equal to the negative reciprocal, which is negative half, okay, of the existing one. So y is equal to negative half x plus c. We still need to try to find c, okay, and then we're going to plug in, we're going to substitute. So sub 4, 5, okay, you sub 4, 5 into the equation. So we got 5, it is equal to negative half, okay, times 4 plus c, okay, so 5, it is equal to negative half times 4 is negative 2 plus c. Therefore, c, it is equal to 7, right? And then we have y equals to negative half x plus 7. Now let's take a look about this second example. Okay, the second example is a little bit more complicated than the first one. By given the 4 points, they ask us to show that the ABCD is a rectangle. Okay, so in order to prove a shape is a rectangle, you probably would start by proving firstly the shape itself, it's a parallelogram, right? So how to prove it's a being parallelogram? You have to prove that the opposite sides are parallel, right? So we firstly need to prove opposite sides are parallel. Then we need to prove that one pair of adjacent sides is perpendicular, right? So then we can prove this is a rectangle. Or you can start with a different approach. You can try to prove the opposite sides are equal, and then you prove a pairs of adjacent sides is perpendicular, right? So there's a different approach. I'm going to using, since we have learned parallels and perpendicular lines with the gradient, so we're going to try to use the first way to approach that. Okay. At the start, we're going to just do a rough sketch, and so that it tells you the rough relationship about the sides and their vertices. Yeah. You don't have to be accurate because you still need to prove it. Yeah. So let's say you have a point A, which is -2, 3. So that's going to be in quadrant 2, right? So let's roughly say this is A. So you have -2, 3. And then we have B, right? B is 0, 4. So that's a 0, that's a B. 0, 4. And then we have C that is 2, 0. And then we have D that is 0, -1. Okay. Okay, so when we connect those points, that we got shapes like this. From the diagram, that it seems like BC should be parallel to AD, AB should parallel to DC, right? Now, we just need to find the gradient between the 2 points, right? So we know that MAB is going to be y2 minus y1, right? y2 minus y1 over x2 minus x1, which is 4 minus 3 over 0 minus, no, be careful here, is -2, yeah? So what we get, this is 1, negative becomes positive, so it's a half, okay? So MCD, which should be equal, let's find out, okay? So MCD is going to be 0 minus -1, and then you have 2 minus 0, which is indeed half. So therefore, MAB, it is equal to MCD. Therefore, AB is parallel to CD. Okay. So similarly, now we're going to prove that BC is parallel to AD. So start with MBC. It is equal to 0 minus 4, and you have the x2, which is 2 minus 0. So just be careful when you plug in the coordinates. Make sure that you're matching. Okay, you're matching with the whichever the point that you consider as the y2 and x2. Okay, so this is going to be -2. All right, -2, and then you have the MAD. MAD is going to be -1 minus 3, and you have 0 minus -2. Okay, so that's going to be -4 over +2. That's also -2. So we say, therefore, MBC, it is equal to MAD. Therefore, BC is parallel to AD. So we have proved that this is a parallelogram. Now we're going to further prove that AB and AD are perpendicular. Okay, so how we're going to prove these two lines are perpendicular? Again, find out MAB. So MAB times MAD, yeah, which is half times -2, that equals to -1. Therefore, AB is perpendicular to AD. Okay, therefore, ABCD is rectangle. All right. So these are the two examples that we using the concept of parallel lines and perpendicular lines in order to find the gradient and also the equation of the straight line. If you got any questions, don't forget to ask me or come to math and numeracy support at lunchtime. Thank you for watching, guys, and we'll see you in next video.